So this is lab 2, motion of a falling object. So in this lab we're going to be tracking the motion of an object falling a short distance, starting from rest. In this case, we're using the empty bag of chips, and we're going to use the data that we gather from Tracker to create ideal models of the system in a setting where there's no other forces except the ones we want to introduce, which are going to be weight, so mass times gravity, and the turbulent drag, which we'll calculate using velocity squared times the drag constant, or as the drag constant. With these forces, that we're going to then use Newton's second law to see how those forces are going to influence the position change of our system. So as you can see here, there's the bag being dropped. So this is some of the data that we gathered from Tracker. The total distance that the bag fell was around 1.2 meters over a span of 0.5 seconds. And I measured out the mass of the bag to be 0.13 kilograms, which is the same as 13 grams. As you can see in the Tracker application there, I did use the bag's length as opposed to like some other object in the room, because I was a little worried that the depth difference between like me and the bag and some other objects might skew the data. But as you can see also, the data does show that we have some acceleration with the curve being arced. So using Newton's second law of motion and the data we gathered from Tracker, I was able to create a model that we'll go over the code next to model and chart these positions, as you can see on the right. So in the above model, you can see that as time progresses, we do have that change in position that is increasingly changing from the acceleration of gravity acting on the bag. For that position model, we have almost exactly the same arc as the model's position versus the real one. But if you look in the one that accounts for drag, there's a larger disparity that you'd expect to happen because there's that increased force acting on our system that would cause the bag to drop slower. I think this is largely due to the fact that the shape and weight of the bag for that time frame didn't really allow drag to influence on our system during that. So here we can see some of the code that I was working with to model the ideal system. So as you can see, we did make those initial changes to the bag with the weight, and the original velocity vector is going to be 0 because obviously we're starting from rest. So gravity is 9.8, obviously. And then we have the drag force constant that we calculated using our velocity and then squaring it in the code right here. Our velocity being the one that we calculated being the average velocity. So as you can see down here, we're including the net force of the bag. So that's going to be Newton's second law, right? You have the mass times the gravity in the direction of the fall. And then this part is accounting for the drag force or turbulent drag acting on the bag. So then we take that and apply it for the change of velocity. So VF equals initial velocity plus F net over mass times delta T. So we calculated the F net acting on our system and then add that to the velocity beforehand during our time interval 0.5 seconds, and then use that velocity times the time change to chart our position. Further, we also have our arrow scale to make the proportion between the drag and gravity force proportional when we have the next image of the model. So as was stated earlier, we definitely have some error being accounted when we look at the disparity between the drag chart and the actual. So I think most of that could be attributed to the bag not being a sphere or some other flatter object and experiencing less drag because of its shape, which if you can like think about the way a bag looks, it's almost like pointed at the end, so that could definitely affect how the drag is affecting it. Additionally, the time frame that I did shoot it in was relatively small with only about 16 frames or so, which could have not given enough time for the drag force to be seen enough. And finally, with the mass of the bag, there were some chips remaining and it could have been too heavy, as was suggested not to be during the instructions, so that could have furthered the issues that we saw with the drag force. So concerning terminal velocity, given the time frame and errors previously stated, I don't believe that the bag saw a terminal velocity being achieved. So with the initial introduction of another force downward, that time frame that it would take for terminal velocity to be reached would certainly be shortened because of the fact that it's already going down at a certain velocity and will take less time to reach that new one. As you can see here, we have the position versus time chart that we showed earlier. But if you look at this, it's not strictly linear, which is why I would say that we probably never reached a terminal velocity.